Warning, the universe has a minimum resolution. We slam into an invisible wall. Add one more bit to a sealed box and reality stutters, like a game maxing out its memory. Temperature jumps, gravity leans in, geometry threatens to fold. That wall isn't software, it's physics. Empty space has a storage limit, and if you push past it, the penalty is curvature. Your memories, the pacing of time, even black holes themselves, nature's error correction, are tied to this limit. Today we trace the Bekenstein Bound, the holographic principle, and the rumor of Planck-scale pixels. Who set the quota? What happens at overflow? To see the wall, we go stand at a horizon. The closet that turns into a black hole. You've got a closet and a compulsion to pack. Every new box you slide in carries a cost. A little more heat from the strain, a little more weight on the floorboards, a little less room to move. That's our intuition for storage. But in physics, the cost isn't just inconvenience, it's gravity. Jacob Bekenstein made a leap that still unsettles. Information isn't an abstract tally. It shows up as entropy. Entropy costs energy, and energy curves spacetime. In other words, bits have weight. And the maximum number of bits you can stash inside a region doesn't scale with the room's volume like we expect. It scales with the area of its boundary. A closet ruled by its door. To see why, follow the poor man's black hole argument. Picture a spherical box, perfectly reflecting, holding radiation and data, hovering outside a black hole. You lower it down on a rope as close as you dare, so you can reclaim as much energy as possible before you drop it in. Then you cut the rope. The box falls and the black hole swallows its contents, every photon, every bit. If the black hole's surface area didn't increase enough to account for those bits, you could lower infinite information with negligible energy and violate the second law of thermodynamics. That can't happen. The horizon's area must rise. Nature updates the boundary, not the interior. Here's the gut punch. The cap on information inside a region is proportional to that region's surface area measured in Planck units. Not cubic meters, square meters divided by the Planck area. Surface dictates capacity. Our 3D habits mislead us. Reality sets the bill at the edge. Now bring it back to a lab. You build a sealed box to store a single bit, just one. You flip a microscopic switch to 1. Landauer's principle steps in like a rent collector. Erasing or reliably writing that bit in a finite temperature environment dumps at least kT ln2 of heat somewhere. That heat is energy. Add enough operations, enough bits, and the box's mass energy ticks upward. Temperature creeps. The more certain you want that bit to be, the more you pay. You can cool the room to lower the price, but cooling itself has a cost. And quantum limits won't let you drive uncertainty to zero without back action. Keep packing. Squeeze more photons, more states, tighter wavelengths. Every attempt to encode finer detail hikes the energy density. At some point, the energy you've confined in your region is so concentrated that the escape velocity at the boundary hits the speed of light. You didn't just fill the closet, you made a horizon. The box becomes a black hole. The ledger switches format. Everything you thought was inside now tallies on the surface area. You tried to store volumes worth of detail. Geometry forced you onto the boundary. There's a twist most people miss. Cross the line and the act of adding another bit doesn't vanish it into nowhere. The horizon expands. The surface area increases to keep the second law safe. The more you demand from storage, the more geometry pays by growing the boundary. This is accounting done with shape. The penalty for overdescription is curvature, and it shows up as a bigger horizon. Meanwhile, something subtle was always happening behind the math. Every plan to jam more structure inside a fixed space means dialing up shorter wavelengths to label more states. But shorter wavelengths mean higher momenta. Higher momenta bring higher energy density. Push far enough and the very probe you use to label a state summons the gravity that hides it. Measurement is part of the packing problem. What nobody knew at the time Bekenstein was thinking this through is how far that area rule would reach. Black holes aren't an exception. They're the strictest enforcers of a rule that whispers everywhere. Nature prices information by surfaces. Entanglement entropy in quantum fields tends to scale with boundary area too. It's a hint that storage rules aren't a quirk of monsters in space. They're baked into the vacuum. Here's a micro story. A graduate student tunes a cavity, trying to trap one more photon in a stable mode. The meter warms, the cooling loop groans, the signal stabilizes, barely. She ekes out one extra bit of distinguishability, but when she runs the numbers, the energy hike that made that bit trustworthy pushed her apparatus closer to the gravitational radius that would end the game entirely. The lab never sees a horizon, of course. But the math that governs their margin is the same math that governs a dying star's last breath. There's a limit, and it's written on a surface. This was the moment everything changed for our intuition. The universe doesn't let you draft endlessly detailed blueprints for what's inside a room. Past a threshold, the room refuses more description by becoming something else. Collapse isn't destruction for its own sake. It's enforcement. You asked for too much. The invoice arrived as curved spacetime. To understand why the bill is written with area, not volume, we need to follow the hint to its logical end. The math points at a surface. The universe points at a length. The Planck pixel, when distance stops getting smaller. Follow the hint to its end and a strange rule shows up. There's a smallest meaningful tick on the ruler. Not a brick wall you crash into, more like the point where the word distance stops carrying information. That scale has a name, Planck length. It's about 1.6 times 10 to the minus 35 meters. If you try to shave below it, the act of measuring scrambles what you're trying to define. Here's the easy-to-hold version. To see smaller things, you use shorter wavelength probes, higher frequency light, sharper beams, tighter focus. But shorter wavelengths carry higher momentum. Higher momentum means more energy concentrated in a smaller region. That energy curves spacetime. Push far enough, and the very probe you chose to reveal detail produces enough curvature to hide it. You try to resolve a distance. A horizon steps between you and the answer. This isn't a trick of the lab. Mead worked it out in thought experiments. Later analyses sharpened the logic, combined quantum uncertainty with gravity, and there's a floor to spatial resolution. Not a literal pixel you could peel off, but a limit on how much position can be specified before the notion of position melts into quantum gravitational noise. It's why physicists talk about quantum foam, Wheeler's phrase for geometry that flickers at tiny scales, like a sea whipped by a storm you can't calm. So what does foam really mean? It means that at Planck distances and Planck times, geometry itself is uncertain. The line you think you're drawing between 2 points frays. Angles wobble. Over big distances, all those jitters average out and space feels smooth. Down in the basement, the floorboards creak. Try to time a photon's flight with an idealized clock, and Wigner's thought limits pop up unless you tie the clock down and let the environment help. Either way, every upgrade you make to precision echoes back as disturbance. Backaction isn't a bug. It's the price of asking. Now remember the earlier lesson. To encode more detail inside a region, you shove in modes with tinier wavelengths. At first, that just raises the energy bill. Keep going, and geometry itself starts acting like a defender. The Bekenstein Bound walks you to a surface. The Planck scale tells you where the game clock runs out. Below that, closer and further, lose operational meaning because any measurement protocol that would tell the difference would create a black hole. People ask, could we catch the foam in the act? Maybe as a faint hiss riding on light from far galaxies. There were ideas to look for wavelength-dependent blurring of distant images, or travel time jitter that would smear sharp pulses. If spacetime had a simple grain, high-energy photons might arrive a touch slower or images would fuzz more than optics allow. Astronomers have hunted for that, and the null results bite. Limits from sharp images and gamma-ray bursts say, if there's foam, it doesn't act like naive gravel. No easy dispersion. No obvious blur. Whatever the microstructure is, it respects Lorentz symmetry to exquisite precision at the energies we can probe within current sensitivities. Down on Earth, people tried to listen with interferometers, machines built to measure absurdly small changes in length. The idea was that if space at tiny scales performed a random walk, the arms of a detector might pick up a correlated noise pattern, a jitter not from thermal drift or seismic hum, but from geometry itself. Those experiments haven't heard a telltale signature. They've turned the dial into constraints instead, ruling out broad classes of simple, holographic noise models and pushing any would-be pixel size down near the Planck area or into more subtle encodings. Absence here is information. It says the code, if there is one, is cleaner than our first guesses. So why call it a pixel if it isn't a grain you can touch? Because the right metaphor isn't sand, it's bitrate. Think of the Planck scale as the maximum resolution unit for spacetime's description that doesn't break the channel. You can oversample an image all day. If the scene itself only contains so much detail, the extra pixels repeat the same information. At sub-Planck attempts, you're oversampling a scene whose fine print is protected by the interplay of uncertainty and gravity. The map can't get sharper without crashing the renderer. Here, S where the earlier surface hint and this minimum length story lock together. If the content that can fit inside a region is ultimately priced by the area of its boundary, then the elementary accounting chip is a patch of that boundary about 1 Planck area in size. The pixel isn't a cube in the bulk. It's a tile on a surface that keeps the books. That's what the equations keep saying, from black hole thermodynamics to how entanglement entropy in quantum fields hugs the area of a cut. The deeper you push into the room, the more you're forced to read the walls. There's a practical sting to this. Every time you design a measurement to squeeze more detail, the Heisenberg toll booth goes up and gravity steps closer. In the lab, that shows up as back-action noise you struggle to cancel. On the edge of a collapsing star, it shows up as a forming horizon. Same rules, different stakes. The world feels smooth and continuous because, averaged out, it is. But underneath, there's a minimum resolution that keeps the show coherent. And if detail really lives on surfaces, then the ultimate surface might be running the whole game. Horizon ledger, where reality writes itself. Stand one hair outside a black hole and think like an accountant. There's no inside you can audit. There's only a boundary, an event horizon, that never shows you a line item directly, but somehow keeps perfect books. That's the weird shift Bekenstein and Hawking forced on us. Reality seems to write to surfaces. Here's the rule the horizon enforces. The number of microstates, the possible arrangements consistent with what you see, scales with the area of that horizon in Planck units. Double the area, double the capacity for distinct states, not because the interior volume doubled, but because the ledger, the surface, got more tiles to write on. Formula has a stark beauty. Entropy equals a quarter of the area measured in Planck areas. It's an area law, and black holes are its strictest auditors. Why a ledger? Because the horizon's job is to separate what you can influence from what you can't. From your side, any attempt to throw in a photon, a notebook, or a star resolves as one change. The horizon's area adjusts. You might never see the notebook again, but you watch the boundary swell by an amount that exactly covers the extra information now hidden from you. You lose access. The ledger gains a bit count. Feel it at the human scale. A single photon climbing toward that surface redshifts, its frequency sags, its identity blurs. The closer it gets, the longer it takes to cross in your clock, the more its energy spreads in your description. When it finally disappears beyond your causal reach, the horizon's area has already nudged upward. One more binary distinction, that photon was either here or gone, has been priced and recorded. You didn't track the interior, you watched the wall update. This is where Hawking radiation sneaks in as a second column in the ledger. Quantum fields near the horizon don't stay empty. Pairs of excitations can become real, with one partner effectively trapped and the other escaping as thermal radiation. That radiation carries entropy away, which means the horizon's area shrinks in step. Deposit information by throwing stuff in. Withdraw by waiting for radiation correlations to leak it back out. The bookkeeping balances, but not in a way that feels intuitive at first, because the digits aren't letters on pages. They're geometric quanta of area. Now scale the stakes. Black holes are the tightest vaults nature builds. Pack too much detail into a region and gravity mints a horizon that guarantees two things. You won't see the insides, and the boundary will remember how much you can't see. It never forgets the total count. The hard question is how the ledger encodes structure. The consensus today leans away from naive erasure. The state of the radiation and the state of the horizon are entangled in subtle ways that can, in principle, reflect what fell in. The page is complete, but the handwriting is encrypted by the dynamics of quantum gravity. Meanwhile, something else was happening in quantum field theory far from black holes. When you split space into two regions and ask how entangled their fields are, the entanglement entropy you compute also scales with the area of the cut between them. No horizon, no singularity, same area law. It's a whisper that the ledger logic isn't a black hole-only rule, it's a habit of the vacuum. The universe seems to count connections across boundaries, not inventory inside rooms. But there's a complication the horizon forces the moment you try to overfill it. Store more and the horizon doesn't bend to your wishes. It grows. The radius increases so the area law keeps pace with your ambition. That's geometry doing enforcement. You demanded more states behind the veil expanded so the bound still holds. It's the same theme we hit in the lab, just turned up. You try to cram detail, reality pays in shape. If surfaces keep the books, then our bulk stories, distance, volume, the feeling of a 3D world, might be playback. That's the unsettling turn the holographic principle makes precise in certain settings. The surface isn't just a receipt, it's the code that can, in principle, reconstruct what the interior does. In the best understood examples, the screen is a boundary where a quantum theory with no gravity lives with negative cosmological constant, as in anti-de Sitter space. And the movie is a gravitational world in one extra dimension. Compute on the edge. Watch a universe evolve inside. People ask for a mental anchor. Try this. You're in a room, and nothing you do to the furniture adds new fundamental digits to the world's description. You can rearrange, you can heat it up, you can write novels. The deep limit to how many distinguishable states that room can support is stamped on the walls. The horizon is the extreme wall. It sets the ultimate rate card for information you can hide from the outside. That flips our storytelling instinct. We want the center to matter most. Nature points us to the border. The ledger writes on area. The tally lives on the edge. And if our 3D lives are priced by 2D boundaries, we have to ask the next question carefully. If the ledger holds the code, are we living in the projection? Two-dimensional universe, three-dimensional lives. If surfaces keep the books, the bolder claim is this. The book can rebuild the story. That's the holographic principle in plain terms. The full physics of a volume can be encoded on a boundary one dimension lower, like a hard drive that stores the movie of a world you then play as 3D experience. In certain universes, we don't just suspect this, we can do the math. On the boundary lives a quantum theory without gravity. Inside emerges a world with gravity and curvature. Compute on the edge, watch geometry answer. Here's the intuition flip. You're in your room. You breathe, pace, talk, think. It feels like the richness lives in the air between the walls. Holography says the fundamental digits, how many truly distinct states that room can host, don't live in the air. They're priced by the surface. The walls hold the code, the volume is playback. Rearrange the furniture and you remix, but you don't mint more underlying capacity than the area allows. So what pushes this beyond metaphor? Start with black holes. Entropy is a quarter of the horizon area in Planck units. That's already a flashing sign that nature counts boundary tiles. Then look at quantum fields here and now. Carve space into two parts and ask how entangled they are. The answer to leading order scales with the area of the cut, not the volume on either side. It's an area law again, far from any singularity. Two big clues. And then the clincher in a special classroom of universes, a duality where a lower dimensional, non-gravitational quantum theory equals a higher dimensional gravitational one. Not resembles, equals. That's a working example of the holographic principle. Human stakes show up fast. If the world's deep description is boundary code, identity, locality, and cause and effect look different under the hood. Yourself isn't a unique bead somewhere in the bulk. It's a robust pattern that the code can support, spread across many boundary degrees of freedom. Locality, the rule that only nearby things interact, may be an efficient summary of how the code organizes correlations, not a bedrock rule. Two regions that feel far in the room can be tightly bound neighbors in the code if entanglement knits them closely. And causality, the arrow of influences, has to match how information can flow on the boundary. The familiar light cones in the bulk are a translation of boundary bandwidth and constraints. Try a microstory. A sealed box sits on a lab bench. You keep pumping in structured light, spin states, phonons. Inside, it never feels fuller in the holographic sense. The lid, your boundary, just has to get denser with code. Each extra distinguishable microstate you try to create inside is paid for by more complex correlations on the surface. You're not filling air, you're saturating a ledger. Here's where the mind protests. If we're encoded on a boundary, where's the screen for our actual cosmos? In the examples we understand best, the boundary is literally, at infinity, a distant surface with clean mathematical properties. Our universe seems to expand with a small positive cosmological constant, not the negative one that makes the math tidy. The screen for our world isn't settled. Some proposals aim at a cosmic boundary tied to the far future, others at horizons associated with observers. The honest state of play. The idea is strong. The exact screen here is under construction. Meanwhile, evidence runs through behavior, not billboards. Black hole area laws don't blink. Entanglement scaling keeps pointing to boundaries. The Ryu-Takayanagi relation in those well-understood AD-SCFT dualities says the entanglement between two regions in the boundary theory equals the area of a minimal surface in the bulk that spans them. That's geometry literally reading out of correlations. Strengthen entanglement on the boundary, and the bulk path between regions shortens. Loosen it, and the path stretches. Distance becomes a function of connection. That flips how you file space. Don't start with a grid and place matter in it. Start with a network of quantum degrees of freedom and their entanglement. Ask what emergent notion best summarizes who talks efficiently to whom. The answer is geometry. The room is the output of the code, not the other way around. Break links in space phrase, knit links in space holds. This changes how we think about error too. If the bulk is playback, smoothness is stability of code words. That's why naive grain searches have come up empty. A good code hides micro errors from macro observers. What you call a table is a high-fidelity pattern resisting noise. You experience solidity because the encoding is redundant and the checks run constantly. None of this makes life less real. It gives it a different kind of real. You're not a smear on a wall. You're a pattern with persistence, protected by constraints that keep chaos at bay. Meaning grows in how efficiently the code carries you forward. And if the world prices detail by area, our next job is to listen for the projector's hum without mistaking the movie for the machine. The screen may be far, but the rules it sets are right here, shaping every scene you live. Experiments chasing spacetime noise. If the code runs on a surface, maybe it leaves a hum. Not a tone you can hear, more like a universal background hiss, geometry's own noise floor. That's where the hunters come in. Experimentalists who build machines that can feel a proton's width change across kilometers and ask if spacetime itself twitches. Start with the idea of holographic noise. If there's a minimum resolution, distances might fluctuate ever so slightly, not as a classical shake, but as an irreducible jitter tied to the information limit. The dream signature wouldn't be random junk. It would be correlated, the kind of pattern two separated detectors would share if they were both reading the same underlying code. Interferometers are the natural stethoscopes. You split a laser beam, send each half down long perpendicular arms, bounce them off mirrors and recombine them. If one arm stretches by a whisper compared to the other, you see fringes shift. Do this with high power, superb mirrors and isolation from the world's rumble, and your device can register distortions smaller than a proton's diameter. That's already how we caught gravitational waves from colliding black holes. The question here is subtler. Is there a residual variance no engineering can scrub, because spacetime itself has a finite bitrate? A few years back, a team tuned two adjacent interferometers, side by side, to hunt for shared noise, correlations that couldn't be blamed on local hardware gremlins. The pitch was simple. If the pixels of space smear positions in a universal way, two independent instruments looking at nearly the same patch of geometry might hear the same murmur. If the murmur was there, it would show up as excess cross-correlation at specific frequencies, beyond what thermal jitter, seismic drift, or electronics could explain. Now here's where reality pushes back. The instruments got cleaner and cleaner, and tentative excesses reported in early analyses did not survive improved background modeling and upgrades. The correlated excess didn't stand up once backgrounds were properly modeled and new knobs were tightened. You can write that as a disappointment. The better way to say it is, those nulls became measurements. They drew a box around entire classes of simple, grainy space models that would have left a telltale blur or dispersion. If geometry has a hum, it isn't a coarse rattle. Meanwhile, astronomers turned the sky into an interferometer of a different kind. If quantum foam slowed higher energy photons even a hair, then light from gamma-ray bursts, catastrophes billions of light-years away, should arrive with energy-dependent delays. You'd see the high-energy photons lag the lower ones as if space were a slightly sticky medium. Observatories stacked events, checked arrival times, and squeezed the uncertainty. The delays didn't show. Within tight bounds, photons of wildly different energies ran neck and neck across cosmic baselines. Simple, speed-of-light through foam stories got pushed off the table, placing strong constraints on Lorentz-violating dispersion. There's another angle, images of distant quasars and active galaxies. If spacetime were a granular lens, scattering would smear points into fuzz beyond what optics and interstellar dust predict. Telescopes pulled crisp fringes from the far universe. The crispness itself set a lower limit on any putative jitter. Space, if it foams, does so with a discipline that keeps Lorentz symmetry intact at scales we can probe. No sloppy hiss. No obvious pixelation in the raw picture, only upper limits on any such effects. Back on Earth, quantum opticians tried squeezing light, reducing uncertainty in one quadrature to beat down shot noise, hoping to pry open a window where any irreducible geometric noise would stand alone. Each upgrade made instruments more sensitive to real physics and less forgiving of fantasy. The more you clean, the more the remaining hiss must be either ordinary or deeply conspiratorial. So far, the remaining hiss is ordinary. Thermal tails, thermal lensing, coding losses, seismic upconversion, quantum radiation pressure noise. The list is long, the fixes are clever, the universe stays quiet. This is where theory re-enters, less as a rescue than as a reframing. If the deep description is an error-correcting code, then naive grain won't leak into macroscopic observables. Good codes hide micro-errors. They don't produce white hiss, they produce stability. Entanglement can stitch fluctuations into patterns that look smooth to any local probe. What would a real signature look like then? Not random jitter, but correlation structured by causality. Specific non-local patterns tied to causal diamonds, or entanglement witnesses encoded in subtle phase relationships between distant detectors. People are working on that. Some proposals sketch cross-correlations between widely separated interferometers that share portions of their causal past. Others aim at tabletop detectors tuned to relational observables, measures that compare two clocks or two rulers in ways that cancel environmental drift, but could expose a shared, geometry-level constraint. There's even work using atom interferometry, where you split matter waves and let them sample spacetime along different paths before recombining, in hopes that any fundamental discreteness would fog the phase predictably. Here's the human moment. An experimentalist spends a month chasing a mysterious bump in the spectrum around a kilohertz. It looks universal. It tempts. She digs into cables, swaps mirrors, changes vacuum pumps, writes code to kill ghosts in the data pipeline. The bump vanishes. It was an aliasing artifact, prosaic, embarrassing, invaluable. Every false whisper trimmed the instrument, and with it, trimmed the space of viable theories. So what did we learn from the hum that didn't show? Two things that matter. First, if there's a minimum resolution, it isn't a gravel road, it's a silk sheet. The code, if it's there, is tidy enough to pass every test we've thrown without scuffing relativity. Second, absence is a compass. It points us toward encodings where information is stored and corrected non-locally, where the right observable isn't a single arm length, but a web of correlations over time and light cones. If we can't hear the noise, maybe the code corrects faster than we can listen. And that suggests a pivot. Stop chasing hiss. Start looking for the logic that keeps the channel so clean. Error correction. Why reality doesn't glitch on you. If spacetime had a crude pixel grid, you'd expect pop-in, stutter artifacts. You don't. Tables feel smooth, planets trace clean arcs, your coffee doesn't tunnel through the desk. The absence of glitches isn't luck. It points to architecture. The deep hunch in modern quantum gravity is that the universe behaves like a quantum error-correcting code. Not metaphor as decoration, but metaphor with teeth. Start with what a code does. Quantum bits are fragile. Touch them and phases drift, states flip, information leaks. Yet we build logical qubits spread across many physical qubits so that small errors don't ruin the message. We add redundancy in patterns that let us detect and correct without learning the message itself. The miracle is that from noise, you can get stability. Now translate that to spacetime. If distance and geometry emerge from entanglement, how degrees of freedom are correlated, then geometry will be as robust as the code that supports those correlations. Local pokes, thermal jitters, microscopic disturbances, get absorbed into patterns that leave the large-scale shape unchanged. That's why naive searches for spacetime grain keep coming up empty. Good codes hide micro-errors from macro observers. Here's the human moment. A quantum lab dials up a surface code on a chip. They push error rates down, measure syndromes, correct on the fly. The logical qubit persists far longer than any single element could. Watching that persistence is like watching a toy spacetime hold together. The lesson isn't that electrons on a chip are spacetime. It's that the recipe, redundancy, locality of checks, non-local storage of logical information, feels eerily suited to the smoothness we see out in the world. Bring in black holes. They're where the code runs hottest. Pack information tight enough and the encoder responds by growing a horizon. That's the storage upgrade enforced by gravity. Hawking radiation then acts like a noisy channel back out. For years the paradox was, does information die? The modern story leans hard the other way. The evaporation process isn't pure white noise. Subtle correlations build over time. The page curve, entropy rising then falling, hints that the ledger is complete. Information is scrambled, not shredded. Scrambling is a code word, literally. Toss a diary into a black hole and you don't get phrases back on the first photons. You get thermal-looking quanta whose joint state, over ridiculous timescales, hides correlations that in principle reconstruct inputs. The black hole is a maximal scrambler. Small errors get smeared, local details get delocalized. That's error correction at its most unforgiving. No early peaks, no shortcuts, but no deletion either. Meanwhile, theory built explicit models where geometry equals code. In certain holographic setups, you can map regions of the boundary theory to regions in the bulk through something called an entanglement wedge. Lose a few boundary degrees of freedom, simulate erasures, and you still recover the bulk operator as long as you have enough of the boundary left. That's textbook quantum error correction speaking geometry's language. Parts of the boundary suffice to reconstruct the interior, others are redundant. The bulk stays stable even when pieces of the boundary are noisy. This structure explains a puzzle from earlier. Why don't interferometers hear a universal hiss? Because local probes couple to local errors, and the code stores the logical geometry non-locally. Local noise mostly tickles gauge redundancies, degrees of description that don't change observables. What would bite is a coordinated pattern of faults spread over a causal region big enough to flip a logical bit of spacetime. Nature seems to keep those patterns rare. There's a cost, though, and we pay it in latency and resources. Error correction burns redundancy. To keep the movie smooth, the code needs headroom. When you try to saturate a region with information, higher energy densities, finer distinctions, headroom vanishes. The code responds by changing the geometry to keep protection. It grows the horizon, dilates time, throttles throughput. Your clock near heavy mass ticks slower because, in effect, more redundancy is engaged to maintain consistency in a high-load region. You felt a tame version on a bad Wi-Fi day. Packet loss rises, protocols add checks, the stream buffers. Frames don't glitch, they pause. Gravity's version is time dilation. Under load, high mass energy, local processes take longer as measured by faraway clocks. The stream stays consistent, it just lags. Here, S where ER equals EPR sneaks into daily meaning. If entanglement knits geometry, then maintaining smooth paths, what you call space, means maintaining patterns of entanglement that resist noise. Two strongly entangled systems behave as if they're closer in the emergent geometry. Break links and roots lengthen, keep links tight and roots hold. In that picture, a wormhole isn't a tunnel you fly through. It's a conjectural correspondence, a cartoon of how entanglement might organize connectivity while keeping causality safe. So why doesn't your world glitch? Because the code is overbuilt where it counts. Redundancy smears microshocks into undetectable gauge wiggles. Local observers see a classical stage because quantum fluctuations are averaged and corrected across many links. When you notice quantum, it's because you've engineered a situation that peels back some protection. Isolated qubits, squeezed states, decoupled environments. Everyday life is the opposite. High error rates tamed by massive redundancy. And when you push the system, try to over-resolve, overstore, overclock, the same architecture that hides errors turns into a wall. Horizons form, clocks lag, channels saturate. Smoothness survives, your ambition doesn't. Consistency has a cost, and we can hit the billable limit. The cost of a bit: energy, time, and the Bekenstein price tag. There's a receipt attached to every bit you trust, not an invoice in dollars, an invoice in heat, time, and gravity. Landauer wrote the baseline number on it. When you erase a bit, or when you force a system into one of two reliably distinct states, you owe at least K times T times ln2 of energy to the environment. At room temperature, that's tiny, but not zero. Cool the room and the price falls, until the cooling machinery and quantum limits on measurement and control climb onto the bill. There's no free ride. Stability costs. Now fuse that with Bekenstein's insight. Information has entropy. Entropy ties to energy. Energy gravitates. So as you raise the certainty of the bits in a device, pushing probabilities toward clean zeros and ones, you pump out heat, stash energy, and in principle raise the device's mass. It's microscopic in a lab register. Scale it, repeat it, accelerate it, and the cost shows up as back action, latency, and if you're reckless with density, curvature. Bits are physical. If you try to forget that, nature reminds you. Here's a micro story. A supercomputer engineer dreams in petabytes per rack and nanoseconds per cycle. She lowers temperatures to trim Landauer's cost, stacks 3D memory to pack more states, routes light for fast interconnects. The profiler looks good until the thermal management plan groans. Fans aren't the limit, heat pipes aren't the limit. It's energy density. Push the toggle rate and you light up error syndromes. Add ECC to catch flips. Now you're spending extra cycles correcting. The average latency climbs. The bit price wasn't just heat, it was time. The machine didn't crash, it buffered. Physics writes the same story with bigger letters. Speeding up reliable state changes means hitting systems harder, measuring sharper, resetting faster. But faster resets dump more heat now. Stronger measurements disturb more. Try to localize all that to one region and the region's energy climbs. The Bekenstein Bound steps in. For a system of energy E contained within a radius R, the entropy S is capped, loosely, by something like E times R in natural units. If you try to encode past that, you're not clever, you're gravitational. The auditor shows up as an event horizon. There's a subtler price tag people miss. Time windows for trust. A bit isn't a platonic label, it's a metastable state you maintain against noise. The longer you demand reliability, the more redundancy or energy you need. Error-correcting codes burn space and cycles up front so that logical information lasts. In gravity's language, stretched reliability under high load looks like time dilation. Load a causal diamond, a finite region where events can exchange signals, with energy and entropy, and the maximum throughput for distinguishable operations within that envelope drops relative to faraway clocks. The stream keeps order by slowing down. Tie this to causality's bandwidth. Light speed caps how fast influences spread. Thermodynamics caps how densely you can pack trusted distinctions per unit energy and temperature. Together, they define a ceiling on computation in a region, a limit on operations per second per cubic meter that stays below the bound where horizons form. The universe doesn't care if your operations are factoring numbers or running synapses. A flip is a flip. A reset is a reset. The bill is universal. Here, S where the lab anecdote meets a black hole. In the device, push clock speeds and bit certainty, and you pay with heat you must export and errors you must correct. When export and correction can't keep up, you throttle. Near a horizon, dump enough information in fast enough, and the geometry itself handles throttling. The horizon swells, the redshift stretches local ticks, and what looked like more bits per second from the inside looks like slower, dimmer, later from the outside. Same story, consistency preserved, ambition taxed. But what about clever hacks, squeeze states, reversible computing, adiabatic tricks? Reversible logic can, in principle, dodge Landauer's erasure cost by never throwing information away. Great, until you need to set initial conditions, correct an error, or interface with a heat bath. Real computation includes garbage cleanup. Squeezing reduces noise in one variable at the price of more in the conjugate. Measurement backaction sneaks in where you thought you saved. The ledger is patient. You can move costs between lines. You can't erase them. There's also a gravitational therefore. Landauer's floor is proportional to temperature. Cool enough, and it's tempting to think you can store cosmic amounts of data for pennies. But the colder you go, the more precious each joule of stray heat becomes, and the harder it is to evacuate without warming your reservoir. Build a giant, ultra-cold memory palace, and the very infrastructure to stabilize it, supports, shielding, energy feeds, adds mass. If you try to hold too much trusted structure inside one radius, you don't just pay with higher utility bills. You summon the auditor. A horizon forms and reprices your assets onto area. So the Bekenstein price tag isn't one number. It's a web tying together KT-ln2 per erased bit, bounds on entropy per energy and size, light speed's rate limit, and gravity's habit of minting horizons when you overfill your cart. It tells you why brains warm, why computers throttle, why experiments can't measure forever without disturbing, and why the universe keeps a ledger on surfaces. And it sets up a dare. Every ceiling invites someone to punch through. But in this system, trying harder is how you meet the wall. Attempts to over-resolve reality, and why they fail. Here's the instinct: if the wall is resolution, push harder. Build brighter lamps, sharper lenses, colder traps. Physics will blink first. That's the rallying cry behind every attempt to over-resolve reality. And for a while, it works. Then the same pattern shows up. The finer you aim, the louder the toll. Start with light. You want to see smaller, so you reach for shorter wavelengths and higher energies. You focus a beam to a spot smaller than a bacterium, then smaller than a virus, then smaller than an atom's orbit. Each gain is intoxicating, and each gain hikes momentum. Momentum means pressure. Pressure means back action. Your probe is now a hammer. The structure you meant to gently read starts to recoil. The act of seeing writes new lines into what you see. So you get clever. You squeezed light in an interferometer to beat down shot noise, trading certainty in one quadrature for uncertainty in the other. Great. You've pushed the noise floor, but the conjugate variable blooms and quantum radiation pressure noise, tiny kicks from photons, begins to shake your mirrors. The meter you trusted becomes part of the system you're measuring. Heisenberg didn't post a speed bump. He built the toll booth into the road. Okay, abandon light. Use particles. Fire electrons with sub-angstrom de Broglie wavelengths. You'll map orbitals, image atoms on surfaces, resolve fine structure. And you do until Coulomb interactions, multiple scattering, and radiation losses churn the target. The beam heals nothing. It inscribes scars. Dial up energy to shorten the wave and you feed fields that push back harder. The price of clarity is disturbance. Push concepts, not just apparatus. Design a jet-Incan probe, a clock and a mirror to triangulate a tiny distance. You shrink the clock to reduce lag, you lighten it to avoid gravity. But too light and quantum jitter broadens the tick. Too heavy and its own gravity swallows the scene. Meade's lesson lands again. Combine quantum uncertainty with gravity and you hit a floor where position stops being a useful word. You don't need folklore, you need arithmetic. Try fields. Create squeezed vacuum states around a test mass, hoping to cancel noise by anti-correlating fluctuations. It works until the anti-correlation couples to a mechanical mode and amplifies motion you can't damp without adding dissipation. Trade-offs nest like Matryoshka dolls. Every cleverness fixes one hiss and reveals another that was hidden by it. The better the trick, the more precise the new bill. What about brute force? Trap more energy in a smaller region so you can label more states. That's the path to lasers so intense they rip virtual pairs out of the vacuum. For a moment it looks like victory. Your resolving power spikes. Then the vacuum talks back. Nonlinearities bloom. The field you created becomes the environment you can't ignore. Drive it harder and the ledger we met earlier shows up. Energy density rises. In principle, if confinement and energy are pushed far enough, the associated gravitational radius would close in and a horizon would form. In labs, horizons don't appear. Apparatus melt first. But the logic is the same at any scale. Every route to finer labels routes through higher energy density, and every such route back reacts. That back reaction is not a nuisance term. It is the limit. Here's a micro story. A team building a next-gen microscope combines electron tachography with adaptive optics and learned priors. Resolution improves beyond what naive optics would permit. Reviewers cheer. Then the calibration run shows a small, systematic bias. The algorithm that denoised the data also hallucinated edges. It didn't over-resolve the world, it overfit the noise. The fix, adding honest error bars, reduced the claimed resolution. The wall wasn't equipment. It was truthfulness about information. So you escalate to gravity's edge. Imagine aiming subplank timing by bouncing light between two mirrors with finesse so high photons make millions of trips. You beat timing jitter down by averaging. But each pass tickles the mirrors with radiation pressure. Collective kicks become correlated motion. You've traded white noise for colored noise that tracks your cleverness. Correlation helps you detect. Correlation helps noise organize against you. What about hacking thermodynamics, reversible computing to dodge Landauer's heat? You can design logic that never erases, stepping through bijection so no bit is lost. Nice in textbooks, fragile in air. Real computation needs initialization and error correction. Errors pile up, you must reset. Reset costs KT-ln2 per bit of true ignorance you throw away. At scale, your erasures dominate. Cooling buys headroom but not amnesty. Exporting heat fast enough becomes the choke point that drags clocks, stretches queues, and enforces patience. The gravest try is the most literal. Concentrate so much energy in a pinpoint that your probe's wavelength is microscopic, then use that to tag sub-Planck features. The moment you try, the curvature you summon closes causal paths. You don't learn more, you make a black hole. What looked like a microscope became an eraser that writes only to the horizon's area. You didn't cheat the Bekenstein Bound, you invoked it. All paths converge on the same scene. Squeeze noise here, it bulges there. Push energy here, geometry leans there. Ask for sharper coordinates and the concept of coordinate phrase. The lost detail doesn't vanish into nonsense. It flows into degrees of freedom you can't address without paying a steeper price, into correlations hidden behind horizons, into entanglement you can't access locally, into time you now have to wait. Every over-resolve attempt becomes a detour to the same wall. Where does that detour detail end up? Not in oblivion. Follow it to the information paradox and the ledger's audit. Follow the detour detail to the horizon and you hit the oldest headache in the ledger's office, the information paradox. Toss a diary into a black hole and wait. Hawking's calculation says the hole glows like a perfect heater, thermal radiation with no memory of what fed it. If the diary specifics never come back, quantum mechanics takes a wound. Pure states would turn into mixed states. Unitarians, the people who swear quantum evolution is reversible, won't allow that. So who's cooking the books? Start with what you actually see. From far away, you watch area rise when you feed the hole. That's the deposit, more hidden microstates, bigger ledger. Then Hawking radiation leaks out. At first glance, it looks featureless. Each photon a coin flip with no hint of a sentence once written on paper. If that were the whole story, the ledger would be losing pages as the horizon shrank. Entropy out, memory gone. But that early story was incomplete. Hawking's original derivation treats the radiation as exactly thermal and independent. Quantum field theory is more slippery. Even if each outgoing quantum looks thermal by itself, subtle correlations can lace them together over time. Think of a choir. One voice sounds like noise. The harmony makes sense only when you hear enough parts at once. If the radiation quanta are entangled in the right pattern, the joint state can, in principle, encode what fell in without any single note betraying the tune. Enter the Page curve, the audit graph everyone argues about. Don Page asked, if evaporation is unitary, how does the entropy of the radiation change with time? His answer sketches a rise, then a peak, around the halfway mark of evaporation, and then a fall back to zero as the hole finishes. Early on, the radiation is entangled with the remaining black hole, so its entropy climbs. After the Page time, the balance shifts. New emissions are more entangled with the already released radiation than with what's left inside, and the entropy of the radiation starts to drop. That curve is the signature of a clean audit. Nothing is destroyed, it's just scrambled and slow. Slow is the operative word. Black holes are extreme scramblers. They mix inputs into non-local patterns at nearly the fastest rate quantum mechanics allows. That's why the ledger looks thermal for so long. To read the code, you'd have to collect ridiculous numbers of Hawking quanta, compare phases with absurd precision, and wait times that make civilizations feel brief. The diary isn't burned, it's shredded, and the shreds are mailed one fiber at a time across eons. Meanwhile, theorists dug for mechanisms, not just metaphors. In holographic models where the boundary theory is manifestly unitary, you can't lose information. Calculations using quantum extremal surfaces showed how the entropy of radiation can be computed by areas in an extended geometry that includes replica wormholes, geometric contributions that effectively allow the radiation to access part of the interior via entanglement. That sounds arcane, but the punchline is practical. The math that once insisted on monotonic thermal growth now produces the Page curve. The ledger balances when you keep the quantum bookkeeping exact. Here's the human version of patience. Imagine trying to audit a corporation that shreds every receipt. then glues microscopic strips into confetti art and ships the pieces across the world by ordinary mail. The law says the records exist. Recovering them is legal and in theory possible. In practice, you'd need to retrieve millions of envelopes, align fibers by grain, and read faint ink under uneven light. That's Hawking radiation decoding. The rulebook survives. Your weekend doesn't. There's a temptation to declare victory and move on. Resist it. The paradox forced clarity about what counts as outside and inside, about when semi-classical gravity fails, and about how entanglement stitches regions together. It also sharpened questions about cloning and firewalls, puzzles about whether the ledger can both keep a smooth interior for an infaller and a faithful record for an outsider without violating the no-cloning theorem. The consensus today bends toward complementarity. Different observers get different but consistent stories, and no single observer sees a contradiction. The code prevents illegal double spending by restricting what any one vantage can access. What nobody knew at the time is how directly entanglement geometry would enter the audit. If ER equals EPR, if entangled systems are connected by non-traversable wormholes in the right language, then the place where information hides isn't a vault you can walk into. It's the pattern of connections themselves. Strengthen the entanglement between the radiation and what remains, and the emergent geometry reshapes so that the route for reconstructing interior operators shifts outward. That's not science fiction. It's the content of entanglement wedge reconstruction in holography. So where did the diary go? Into correlations on the boundary of what you can touch, into phases that take ages to line up, into a ledger that never forgets but never hurries. The audit doesn't find a smoking hole with ash. It finds an account that debits area, credits radiation entropy, and after the page time, starts writing refunds in correlations you can't cash quickly. The universe keeps every receipt. It just files them where impatience can't reach. And if the book is shut for you, if no single observer can open all the pages at once, maybe the right tool isn't a crowbar. It's entanglement itself. If connectivity builds space, perhaps connectivity also gives us the keys to read what the ledger wrote. Entanglement builds space, threads that weave geometry. We've been circling the ledger and the audit. Now we pull the thread that ties it all together, entanglement as the fabric maker. The claim sounds bold but lands cleanly once you see the pattern. Connectivity of quantum states isn't riding on geometry, it's writing geometry. Start small. 2 qubits maximally entangled behave like one system spread across 2 labs. Change the basis in one and correlations flip in the other with no signal sent. No speeds are broken, no messages jump. Still, closeness shows up as perfect predictability in joint measurements. That's the seed of the idea. Closeness can mean correlation, not coordinates. Scale up to many-body systems. Take a quantum state on a lattice. Where entanglement is dense and structured, certain observables propagate efficiently. Where it's sparse, influence dies quick. Draw a graph with nodes for degrees of freedom and weighted edges for entanglement strength. What emerges is a map of who talks to whom that looks suspiciously like a curved space. Strengthen links, paths short. Weaken them, paths lengthen. Distance stops being input and becomes output. Here's the human-scale micro-story. 2 labs miles apart share halves of many entangled photon pairs. Each lab also couples those photons to local matter qubits, tiny spins in diamond. On paper, by ratcheting up the entanglement between their registers, the graph distance between certain logical operations drops. Protocols that would be slow with weak links become near-instant logical moves because the joint state already carries the heavy lift. The room didn't bend. The resource that measures distance did. This intuition gets teeth in holography. In those dualities where a boundary quantum theory equals a bulk gravity theory, the entanglement entropy of a boundary region equals the area of a minimal surface that hangs into the bulk Ryu-Takeyanaga's bridge. Change the boundary state so 2 regions share more entanglement and the minimal surface between them shrinks. Translation: the bulk distance shrinks. Geometry is reading from correlations. The math is explicit, the picture is crisp. Now bring in ER equals EPR, the conjecture that entangled systems correspond in the gravity language to non-traversable wormholes. Not sci-fi tunnels you can fly through, but a statement about connectivity. When two black holes are maximally entangled, their joint description looks like a smooth bridge between horizons. No messages can pass faster than light. Causality stays locked. But the most efficient description of their joint state organizes itself as a connected geometry. Entanglement didn't ride the bridge, it was the bridge. Here, where it gets practical. In entanglement wedge reconstruction, you can recover bulk operators, things, happening inside the gravitational region by acting only on the right chunk of boundary degrees of freedom. Lose part of the boundary, erase data, and you can still pull out the interior as long as you hold enough of what remains. That's quantum error correction with a map. The code stores interior information redundantly across the boundary, and entanglement decides which boundary swath controls which interior patch. Space is the bookkeeping of which reconstructions overlap. Stakes appear as soon as you tug a link. Break entanglement across a cut and the corresponding minimal surface area grows. The emergent distance inflates. Push hard enough and formerly connected regions drift so far apart in the bulk that efficient reconstruction fails. They fall out of each other's entanglement wedges. In plain terms, correlations don't just flavor space, they hold it together. Fray them and space unweaves. Complications sharpen the point. You can crank up entanglement indiscriminately and not always get a tighter, well-behaved geometry. Structure matters. The right pattern, short-range entanglement with controlled long-range tails, gives you a smooth manifold with a sensible light cone structure. Junk entanglement produces spaghetti connectivity. No clean distances, no causal order you trust. Smooth space is coded entanglement, not maximal entanglement. Parallel action. While holography cranks through minimal surfaces, many body physicists map tensor networks, MERA, PEPS hyperbolic tilings, that naturally represent ground states with area law entanglement. Those networks look like discretized curved spaces. Causal cones in the network echo like cones, geodesic lengths count bonds. It's a toy lab where distance is literally how many entangling gates you must traverse to relate two sites. Fewer gates, closer points. Add gates in the right places, and you curve the network. What nobody knew at the time is how deeply this view would reframe puzzles about locality. In gauge theories and gravity, there are redundancies, different descriptions of the same physics. Entanglement-based reconstructions respect those redundancies automatically. Bulk operators are defined up to gauge moves, and only their action on code subspaces, the protected logical degrees, matters. Locality becomes the statement that logical operators factorize approximately when entanglement is arranged in bands, not that fields live on pre-drawn coordinates. Human moment. A theorist draws a minimal surface on a whiteboard to compute an entropy, then realizes she's also drawn the tightest thread bundle tying two regions together. The area she shades is a measure of how many qubits of connection hold the bridge. She adds one more EPR pair across the cut, watches the surface shrink in the math, and mutters, "Closer." No ruler moved. The relation did. Impact lands like this. If connectivity builds space, then bandwidth, how much, how fast, and how cleanly entanglement can be maintained, sets the power of regions to influence each other. Bottlenecks become geometric necks. Throughput limits in quantum channels map to causal limits in the bulk. And when you overload the links, the code pushes back by reshaping geometry, stretching times, inflating distances, or minting horizons. Networks have bandwidth, and bottlenecks define power. Bandwidth of reality, light cones, causality, and finite throughput. If entanglement lays down the roads, causality sets the speed limit and the toll booths. Light cones aren't just diagrams in textbooks, they're envelopes that say who can talk to whom and when. Draw one around an event, a flash, a choice, a flip of a bit, and it's a diamond in spacetime. All the points that can influence it, and all the points it can influence. That diamond is a data envelope. Nothing outside sends in updates fast enough. Nothing inside broadcasts beyond its rim without time to spare. Throughput is finite by design. Light speed is more than a number. It's the maximum rate at which reliable distinctions, bits that someone could in principal use, can propagate. Photons aren't special because they're fast. They're special because they saturate the channel without carrying rest mass that would slow them. Every other messenger, atoms, pulses in fiber, whispers between neurons, rides below that ceiling. If geometry is a network built from entanglement, light cones are the network's routing policy. No packet jumps ahead of the wavefront that defines now later. Here's a human-scale micro-story. Two labs share entangled pairs in a classical line. They prearrange a protocol, measure here, announce later, compare notes at a meeting point. The quantum correlations look instantaneous in raw coincidences, but no usable message arrives before the classical call. They live inside a causal diamond bounded by the speed of light and their clocks. The protocol works because the bandwidth budget is respected. Try to treat correlations as a shortcut and the meeting falls apart. No pattern, no meaning, no cheat. Bandwidth isn't just distance over time. It's energy over temperature over accuracy. To send a bit you trust, you need separation in states bigger than the noise that could flip them. Landauer's price tag shows up as heat you must dump to keep errors in check. Push the bit rate, and you pay in energy. At some point, energy density along your link climbs and gravity starts to matter. Channels have capacity. Cram too much coded structure into a causal diamond and you don't get more news across. You redshift your own signal. The local clock lags. The channel preserves order by slowing throughput. Meanwhile, something else is happening that our diagrams usually hide. When you draw two diamonds that barely touch, you're drawing two communities whose updates don't quite sync. That sliver of non-overlap is ignorance baked into the world. Events there can't be resolved here yet. It isn't a bug. It's what lets separate regions compute in parallel without tripping over each other's partial results. Global simultaneity would demand infinite bandwidth. The universe chooses localism. Small diamonds, high fidelity. Big diamonds, lower apparent update rate. Complications kick in when you start optimizing. You can compress messages with clever codes, piggybacking multiple distinctions on fewer carriers. Great, you've raised effective throughput. But compression depends on shared context, which itself had to be established within past cones. Bootstrap too aggressively and you discover a hidden cost. The better your compression, the more fragile your pipeline to noise, and the more you must spend on error correction. Those cycles eat time. The causal budget doesn't budge. Zoom out to gravity's servers. A massive object sits between two regions trying to talk. Their light cones still meet, but the geodesic's curve, signals redshift, and arrival time stretch. From far away, it looks like the link lost bandwidth. From inside the well, it feels like the clock slowed. Both are the same statement. Energy has occupied the network and reserved resources for consistency. The more mass in the diamond, the more redundancy the code throws at stability. The thicker the error-correcting layer, the slower the net tick for outsiders. There's a punchline that hides in plain sight. Attention, the way you allocate your own limited processing mirrors causal bandwidth. Your brain can't broadcast high-resolution updates everywhere at once. It routes salience through priority cones. What's near gets cycles. What's far is summarized until needed. Miss a turn because your focus was saturated. That's a local diamond deciding not to forward an update until later. Biology learned the same lesson physics enforces. Finite channels demand triage. Impact lands in three pieces. First, no influence updates the entire universe at once. Even the fastest news respects cones. Second, there's a rate limit to trustworthy change. Energy, temperature, and geometry conspire to cap operations in any causal diamond before horizons or lags take over. Third, bottlenecks aren't annoyances. They're the shapes that define power. A narrow neck in the entanglement network becomes a geometric neck in the bulk. Control the neck, and you control how fast stories can cross it. You can feel the T's building. If bandwidth throttles updates, what happens when you flood the channel until every path is busy, every check engaged, every clock heavy? We've seen space stretch under load. Now when the clock lags, itself, time under maximum load. We've talked about bandwidth and cones. Now feel what happens to the clock when the channel saturates. Load a region with information, energy you're tracking, distinctions you refuse to lose, and the local tempo changes. That's gravity's most human signal, time dilation. The more mass energy you marshal inside a causal diamond, the more the redshift stretches the rhythm of events for outsiders. It isn't a metaphor. It's the ledger forcing patience to keep consistency. Start with the clean case. Put a clock high on a mountain and another at sea level. The higher one runs faster. Same atoms, same transitions, different gravitational potential. In the language we've been building, the low clock sits in a busier diamond. More energy, more curvature, more redundancy engaged to hold smooth geometry under stress. From far away, its ticks arrive late, like frames queued on an overworked server. Nothing broke. The protocol added checks. Push the intuition into the extreme. Near a black hole's horizon from your distant perch, every process in the well crawls. Signals you send down arrive with less punch. Signals that climb back are drained and delayed. Locally, nothing feels odd. Your lab on a tether runs fine by its own clock. But cross-compare with the far world and latencies explode. That's what a saturated channel looks like when geometry carries the accounting. There's a lab-scale taste of this in any system near limits. Pack memory bits densely at low temperature, keep them clean with error correction, and your controller spends more cycles maintaining trust than flipping new states. The device doesn't spit out garbage, it slows so outputs remain reliable. Heat pipes groan, ECC lights blink, watchdog timers stretch. Under maximum load, liveness yields to consistency. The same trade surfaces in relativity as the gravitational redshift formula you can write on a napkin. Climbing out of a potential well multiplies time intervals by a factor set by geometry. You don't need the algebra here, you need the logic. Energy density claims resources. Resources claimed by stability aren't available for speed. The code assigns budget where it must. First to keep causal order, second to keep clocks in step locally, only then to accelerate throughput as seen from afar. There's a deeper crack that opens when load spikes. Synchronization fails globally. In a flat, empty universe, you could pretend there's a universal now. Add curvature and finite signaling, and attempts to stamp moments everywhere at once smear. Two observers, each honest in their frame, won't agree on slices of simultaneity that cover a busy cosmos. That fracture isn't a bug. It's how the network avoids contradictions when updates can't propagate instantly. Here's the human moment. You wait for a reply from a friend on the far side of the planet during a storm that's hammering undersea cables. Messages go, but retries multiply. Your screen shows typing for minutes. The app doesn't push nonsense. It holds until packets confirm. That pause saves meaning. Gravity's delay is the universe's typing indicator when regions run hot. Bring in the Bekenstein price tag and it sharpens. Each bit you erase or lock in costs kT ln2 of heat you must manage, and every joule added to your diamond deepens the well. Try to sustain a high rate of clean operations in a tight region, and you face the same paired wall. Waste heat you can't expel fast enough and curvature that stretches your link to the outside. Time under load is how the ledger keeps your computation from forking realities. Now stitch in the entanglement view. If connectivity builds space, maintaining clean, structured entanglement under attack requires constant syndrome measurements and corrections. Logical moves spread across many degrees of freedom. Those take time. In the bulk translation, preserving smooth geometry in a noisy, energy-dense region maps to longer proper times per trusted update. Strengthen protection, accept latency, loosen it, risk glitches you'll never forgive. Meanwhile, something else was happening at horizons. As infalling matter raises the area, the ledger's storage, the exterior description redshifts every interior tick. Evaporation drips information out as correlations over ages. The clock lag is the user interface of the audit. You can preserve unitarity, but you can't demand instant readout. Maximum load enforces slow release. Edge cases tempt. What if you root around lag with clever encodings? Use entanglement to shortcut time. Protocols like teleportation feel like cheats until you tally resources. You still need classical bits sent at light speed and pre-shared entanglement established in past cones. The invoice always includes propagation and prep. No message outruns its causal diamond. No process beats its thermal budget. Impact lands on choices. Every decision you make writes to a constrained ledger in a finite envelope. Attention splits bandwidth, memory burns energy, coordination across distance pays in waiting. In traffic and markets and brains, you see the same curves. Under light load, response is snappy. Push toward saturation, cues form. Beyond that, systems either lag or fail. Nature chose lag. That's the quiet mercy. Instead of tearing, the fabric buffers. Frames don't drop. Clocks drift apart in a lawful way. Near mass, you feel weight. In time, you feel weight. The minimum resolution that kept space from overfitting its own noise now keeps time from fracturing under pressure. And if lag is baked into the ledger, there's one more question to ask. When time stretches under load, what does that do to choice? Living in a finite resolution world. If time lags under load, choice has to live inside that lag. Every decision you make is a write to a constrained ledger within a causal diamond that can't broadcast everywhere at once. That's not doom. It's guidance. It tells you which moves are costly, which are cheap, and why attention, your private bandwidth, matters like energy. Start small. You wake up and check your phone. 10 pings wait. You can't open them all at once and still understand them. Your brain routes by salience. That's a bandwidth allocation problem dressed as a morning routine. The physics word for it is compression. You throw away most of the incoming detail, keep what's predictive, and store only the bits you can protect against noise. That's culture too. A poem isn't infinite description. It's a compressed code that reconstructs feeling reliably across noisy minds. This is where the finite resolution world starts to feel like an ethics class. If attention is limited and writing stable bits costs energy and time, then what you give cycles to becomes a moral choice. Ragebait burns bandwidth without preserving meaning. Quiet craft, learning, teaching, repairing, writes fewer bits, but they last longer and compress better. In a universe priced by area and protected by codes, elegance beats maximalism. Signal over noise isn't a slogan, it's a survival rule. Tech runs into the same wall in louder ways. You can buy faster GPUs and cooler data centers, but Landauer's rent shows up on every invoice. Erase more, spend more. Correct more, wait more. Quantum computing won't cancel the bill, it just pays in different columns. Coherence time, cryogenics, error syndromes. The dream is speed up for special tasks, but the guardrails don't move. Limited causal diamonds, finite heat budgets, geometry that mints horizons if you try to hoard too much trust in one place. Here's a micro story. A startup promises infinite scroll learning, a model that digests the whole internet and serves perfect answers instantly. The demo dazzles. Then the latency graphs come in. At scale, the system thrashes. Cache misses, memory pressure, thermal throttling. Engineers add smarter retrieval, finer-grained caching, distillation to shrink context windows. The product stabilizes when it stops trying to know everything at once and starts compressing what it serves to the tasks people actually do. The win wasn't more bits, it was better encoding. Personal identity fits the same template. You aren't a continuous torrent of detail. You're a high-fidelity pattern held against noise by redundancy, habits, relationships, stories others can help you reconstruct when you falter. Memory forgets. That's not failure, it's compression. You keep the summaries that predict what matters next. The ledger won't store infinite subplots about you. It'll keep the motifs that let the next chapter make sense. Creativity inside limits gets sharper, not duller. Painters work on finite canvases. Composers score for instruments with bounded ranges. Constraints force structure. In physics, holography says walls price capacity. In art, frames price attention. The best work exploits redundancy, motifs, symmetry, callbacks, to carry meaning further than raw bandwidth would allow. The code does the lifting, not the volume of paint. There's a civic version of this too. Societies with infinite broadcast and zero compression drown. Misinformation thrives because verifying costs more bits than inventing. The fix isn't to shout louder, it's to build error correction into institutions. Redundant checks, slow deliberation when stakes are high, fast heuristics when they're low. That looks like bureaucracy until you remember the alternative is a black hole of trust where every rumor free falls. Meanwhile, future tech will keep sprinting at the wall. Sensors will get sharper, models bigger, networks denser. Great. The game won't be brute force, it'll be choreography. Put computation where cooling is cheap. Route data along geometries that avoid hot bottlenecks. Use reversible steps where you can to spare heat, accept erasures where you must, and budget them. Most of all, stop worshipping resolution for its own sake. Ask what distinctions are worth paying for. Human moment. You're at a bedside holding a parent's hand. The room is quiet, monitors blink. Your phone buzzes and you mute it. In a finite resolution world, that silence is a choice to allocate scarce bandwidth to a pattern you refuse to lose. You rehearse a story they told you as a kid. They smile. That right is small in bits, enormous in meaning, and so well encoded across people that it can outlive bodies. Wisdom starts to sound like engineering. It's picking compressions that won't betray you under noise. It's knowing which details to drop so the message survives. It's refusing to hoard when hoarding summons the auditor. It's investing in redundancy, community, documentation, apprenticeship, so patterns persist when elements fail. It's designing rituals that refresh entanglement between people, so the emergent space between them stays navigable. None of this shrinks wonder. Limits give shape. A minimum resolution makes the world legible. You can lean on that. Build codes that honor it. Tell stories that use it. Spend attention like the moral resource it is. And when you hit the wall, don't curse it. Listen. It's the edge that keeps the movie in focus. We've circled the wall from physics to life. One last step remains, naming the line we won't cross and what the limit says about us. The final error, what the minimum resolution means. Surfaces, codes, bandwidth, lag, one operating system. The minimum resolution isn't a cage, it's scaffolding. You're a high-fidelity pattern held against noise by redundancy, habits, bodies, friendships, archives. Mortality looks different here. Graceful degradation, not cosmic deletion. Some details fade. The code preserves what lets the story continue. Where's the screen? Honest answer, unsettled. Our universe's boundary isn't the tidy one in textbooks. That's fine. The behaviors, area pricing, entanglement geometry, error correction speak louder than a map. Equals EPR stays a guide, not a shortcut. Speculation flagged. The screen might be an asymptotic ledger tied to boundaries at infinity and observer-dependent horizons, invisible locally because good codes hide their scaffolds. If so, all lives in limits. Miracles aren't needed, discipline is. Here's the line I won't cross, trading mystery for mythology. The wall isn't an ending, it's the rule that keeps meaning coherent. Limits give reality shape. Without them, stories fall apart. Want the next layer, the link between attention, entropy, and memory? Watch the follow-up next. Subscribe for more untold edges.